Okay, so hello class, welcome back. So in this recording, we're going to take a look at the second section of chapter 12, which is section 12.2, test for independent and test for homogeneities of proportion. So we're going to use the same shortcut for the two different types of tests. We're going to test for independent and we test for homogeneities of proportion. So let's take a look at the first test that we have in this recording, was a test for independent. So in which case, we're going to use in the test for independent. So in a contingency table, so we're going to use in a table then. So in a contingency table, we have two qualitative or categorical variables, and we often wish to determine if the two variables are related in some ways. So that's going to be the idea for test for independence. So when you have two qualitative variables or categorical variables, and you want to determine if they are related or they're going to be not related at all. So that's going to be the test for independent. So the test used to determine if there is an association between the row variables and the column variables in a contingency tables is called the chi-square test for independent. So if you want to determine if the variable, the row variables and the column variables in a contingency tables is somehow related or related in some ways, then we're gonna use the chi-square test for independent. So because it's gonna be the test for independence, so how you gonna say the known and the alternative hypothesis? So the known hypothesis, HO, we're gonna say that the two variables are not associated or they're gonna be independent. For the alternative hypothesis, H1, we're gonna say that the two variables are associated or they're gonna be dependent. So that's gonna be the idea for the test of independent. So the known hypothesis, we're gonna say that the row variables and the column variable, they are independent. For the alternative hypothesis, we're going to say that the row variables and the column variable, they are dependent. So the idea behind testing these types of claims is to compare the actual counts to the expected counts. So it's kind of similar with the previous recording 12.1, right? We're going to compare the actual count, which is the observed, and the expected count, which is what we expected if the known hypothesis is true, okay? So if a significant difference between the actual counts and the expected counts exists, we would take this as an evidence against the known, which means that we're going to reject the knowns if there is a significant difference between these expected counts and the observed. So we're going to compare the difference between the observed and expected, right? So the observed would mean that the value that we actually have it from the sample. So that should be easy. The question should give you that observed. Now, based on the observed, how we're going to calculate the expected so we can compare them, right? So this is the formula that we might use it for the calculation of the expected frequency. So expected frequency in a chi-square test for independent. So this is how we determine the expected count for a chi-square test for independent. So in order to find the expected frequency in a cell when performing a chi-square test for independent test, we multiply the cell row total by the column row totals and then divide this result by the table total. So we multiply the row total by the column totals and divide this result by the table total. So this is gonna be the formula. Expected frequency is equal row total times the column total divided by the table total. Okay, so that's how we determine the expected. The observed should be given from the question, so you don't have to worry about that. The question is gonna give you the observed values. Now, the only thing that's based on the given table of the observed, we're gonna calculate the expected. And then the formula is given like this, right? So we're gonna take the total of the rows, multiply with the total of the column and divide it by the table total. So you have to determine the row total, the column totals, and the table total before we can actually find the expected frequency for each of the cells in the table. So for example, let's take a look at this given table. So those values gonna be the observed, that's what we have. So category number 1, 2, and 3, and this is gonna be success and failures, right? So before we can find out the expected frequency for each of the cells in this table, you have to get the total, right? So I need to get the total for the row, and I need to get the total for the columns, right? Now for the row totals, we're gonna just add everything horizontally. So this is gonna be the first row, this is gonna be the second row. So we're gonna add the first row, everything on the first row to get the total for the first row, everything for the second row to get the total for the second row. So let's see what's gonna be the total for the first rows and the second row. So 204 plus 199 plus 214, yeah. So that's going to be 617. So I'm going to put the answer right here, 617. That's going to be the total for the first row. Now, similar idea, 96 plus 121 plus 89 to get the total for the second row. So going to be 315. Yeah. So that's going to be 315. So that's going to be the row total, right? So the total for the first row, the total for the second row. Now, similar ideas, I'm going to do the total for the first column. So what's the total for the first column? We got 204 plus 96. So that's going to be 300. So that's going to be the 300 for the first column. Similar ideas, I'm going to do 199 plus 121. That's going to be the answer for the second column, which is 312 or 20. Yeah, 320. And now for the third column, we're going to get 214 plus 98, which is equal to 312. Yeah. Now, in order to get the table total, you can add on up the row or you can add on up the column, the total of the rows together or the total of the column together, one or the other, right? Or you can add on up the number inside the table right here. Yeah, so you can add on up the answer, on up the numbers inside the table. That's going to be the table total. So going to be 204 plus 199 plus 214 plus 96 plus 121 plus 89. Okay, so this is going to be the table total, 932. So 932. So that's how we got the table totals, or you can do another way to get the table totals, the total for one of the rows. So the first row is 617 plus the second row is 315. That's going to be 932. So that's another way to get the table total. Or you can add the total for one of the row to the column together. Then the first column is 300. The second column is 320. The next one is 312. All of the column together also give you 933. So that's how we got the row total, the column totals, and the table totals. Now, based on the calculation of the row, the column, and then the table total, now we're going to go back to every single cell right here and determine the expected frequency for each of the cell then. Now, for the first one right here, the expected frequency is equal to the row total. So this on the first row, so the row total will be 617 times it by the table total, the column total. So this on column 1, so the column total will be 300 divided by the table totals is 932. 617, yeah, times it by 300 divided by the table totals is 932. Then we're gonna get the expected. I'm gonna give you 2 decimal place because I don't have enough rooms over here, right? So just give you 2 decimal place, 198.61. So 198.61, 198.61. Okay. So that's gonna be the expected frequency for the first cell. Now we're gonna move on to the next cell right here, and we're gonna use a similar idea to calculate the expected, right? Now it's equal the row total. So this cell's on the first row. So the row totals is still 617. Multiply with the column total. The column totals is now equal to 320. Divided by the table totals is 932. Okay, so the table totals won't change it. Okay, so 617 times it by 320 and then divided by 932. Okay. 211.85, 211.85. Yeah, so going to be 211.85. Now, similar idea we can do for the next one, right? You guys got the idea how we calculate the expected frequency for each of the cells in the table, right? So for the third one, it's going to be row total. It's still on row number 1. So the row total is 617 times it by the column totals is 312 divided by the table totals is 932. Now we're going to use a calculator to get this answer then. 617 times it by 312 divided by 932. 206.55, 206.55, yeah. Now that's gonna be the expected value for the first row. Now similar idea, we're gonna do the expected value, expected frequency for the second row. Now row total will be 315 times it by the column totals is gonna be 300 divided by the table totals is 932. Okay. So let's calculate this then. So gonna be 315 times it by 300 divided by 932. 101.39. So it can be 101.39. Okay. Now, similar idea, we can move on to the next calculation, right? So it's going to be row totals. It's going to be row number 2. So 315 times it by column total. It's going to be 320 divided by the table total, 932. Okay. Now it's going to be 315 times it by 320 divided by 932. 32. So going to be 108.15, 108.15. Okay. Now one more to go, right? So similar idea, we're going to calculate the expected frequency for this cell. Row totals, the column total divided by the table total. So row totals is 315 times it by the column totals is 312 divided by the table totals is 932. Okay, let's give it a try. Let's see what is it then. So 315 times it by 312 divided by 932. Okay, 315, 312, 932. So that's going to be 105.45, 105.45, 105.45. Okay, so that's how we're using the formula to calculate expected frequency for each of the cells in this contingency table. So the expected frequency is equal the total of the row times it by the total of the column divided by the table total. Yeah. So when you take a look at the cell right here, you have to find out the row total and then the column totals and then divided by the table totals. Excuse me, that's going to be the values at the corner right here, 932. So that's going to be the one of the step in your hypothesis test. You might do this calculation by hand, or you can use a shortcut and can get the answer directly. So this is how we calculate the expected frequency from a contingency table. But when you're using the shortcut, you don't really have to calculate the expected frequency because the shortcut will help you with this calculation. So we don't really have to calculate this by hand yet. Okay, so after we got the idea, right? So after we know how to calculate expected frequency, now we're going to talk about the hypothesis test for independent. So step number 1, we need to, or step number 0, you have to check the condition. So let's see what's going to be the condition for the test of independent. So the first condition or the first requirement you want to make sure is the samples are obtained using simple random sampling. So make sure that the sample that we selected going to be at random. The second requirement is all of the expected frequencies are greater than or equal to 1. So all of the expected frequency should be more than or equal to 1, at least 1. No more than 20% of the expected frequencies are less than 5. So no more than 20% of the expected frequencies are less than 5. So that's going to be the third requirement. It's similar with the condition that we have in the previous recording, right? So 12.1. So that's going to be the requirement. After we double check the requirements, and if they are good, we can move on to the hypothesis. So now we're going to talk about step number 1. So how we're going to state the known and the alternative hypothesis for the test of independent. So for the known hypothesis, we're going to say that the two variables are independent. Yeah. So the row variables and the column variable, they are independent because this is the test for independent. For the alternative hypothesis, we're going to say that the row variables and the column variables are dependent. Okay, so it's going to be dependent or they somehow related. So that's going to be step number 1, determine the known and alternative hypothesis. Known hypothesis, the two variables are independent. The alternative hypothesis, the two variables going to be dependent. Now, step number 2. We're going to determine the significant level alpha based on the seriousness of making type number 1 error. So select an alpha. Most of the time, alpha should be given. If they don't, then you might use an alpha is equal 5%, 0.05. Now, step number 3, you have to calculate expected frequency, right? For each of the cells in the table. So you might use in the formula that we just try it, right? So the row total times the column total divided by the table total to get the answer for one of the expected frequency. Or you can use in a shortcut, yeah. After we got the expected frequency, then we can calculate the test statistic, and this is the formula. So we're gonna use a calculator then. So this is gonna be the formula to calculate the test statistic. It's similar with the formula that we learned from the previous recording also. It's gonna be equal to the summation of OI minus EI squared divided by EI. So observed minus expected raised to the power 2 divided by expected, and we're going to repeat for every single case in that table, every single cells in that given contingency table. Now, this is going to be the chi-square distribution, so we have to determine the degrees of freedom. So we got two variables, row variables and column variable, right? So now how we determine the degrees of freedom? So this is how we determine the degrees of freedom. We're going to take the numbers of row minus 1 times it by the numbers of column minus 1. That's going to be the degrees of freedom. So take the numbers of rows in the table minus 1. Take the numbers of column in the table minus 1 and multiply those two numbers together to get the degrees of freedom. Okay, for the chi-square distribution. So that's going to be step number 3. We're going to calculate the test statistic, right? So you might use a calculator to get the answer of this, okay? Now, after we got the test statistic, now step number 4, we're gonna use a shortcut to calculate the p-values, or we calculate the p-values, right? And then the shortcut we're gonna use it's gonna be the chi-square test. So the chi-square test is the shortcut that we use it for the test for the p-values of the test for independent. So you have to input the matrix because we have the rows and the columns. So you have to input the matrix. So this is how we input the values onto a matrix. You're going to go second, x to the power -1 to accept the matrix. Yeah. So let's follow that step right there. We're going to go second, and then the x minus 1 on top of that will be the matrix option. So select that. And then we're going to go to the edit option. And then whatever the matrix that you want to edit, just select them. So I'm going to use it just look like matrix A. Yeah, so most of the time. Now, after you go to the matrix A, now the calculator will waiting for your indication of the numbers of row and the numbers of column. It's always go in that order, the numbers of rows and then the numbers of column. So for example, you might take a look up your table right here, right? So for this table, we got 2 rows and then 3 columns. So you're going to change it. Oh, my table have 2 rows, enter, and then 3 columns, enter. Now, after you select the dimension of the table with the numbers of rows and the numbers of columns, the calculator will modify accordingly, right? So we have 2 rows and 3 columns. So the first observed value we have is 204. I'm going to put the observed in the matrix A. And then the next one is 199. The next one is 214. The next one is 96. The next one is going to be 121. And the next one is 98. So this is going to be the observed matrix A. So that's how you input the matrix. So once again, we're gonna go second x to the power -1 to accept the matrix. And then we're gonna go to the edit option and select matrix A and input the numbers of row for the matrix A and the numbers of column for the matrix A. You have to follow that order, row and columns. After you input the rows and columns, the calculator will modify the matrix. And after you got the matrix, you just input the value for each of the cell that we have. You just input the observed values. Yeah. So that's how we input the matrix, right? So after we're done, we're gonna go stat, and then we're gonna go test, and we're gonna go to the chi-square test. So after you're done with the matrix, you might go second quit, and then stat, and then test, and then chi-square test. There you go, option C, chi-square test. Now the observer is gonna be the matrix A, right? So it's already have the matrix A, so that's easy. And then the expected will be matrix B, yeah. So observer is gonna be matrix A, and then the expected is gonna be matrix B. You only need to input the observed. The expected, the calculator will take care of that. The expected matrix, the calculator will take care of that. After you run the shortcut or after you're using the program, the calculator will update the matrix B. So the only matrix that you have to input is matrix A. Now, if you want to call the matrix, right? So if you don't have the matrix right here, right? And you want to show this in matrix A, you're gonna go second matrix, and then go down to the name of the matrix that you want to call that, so matrix A. And then after that, we're gonna go down to the calculate. That's really much. Oh, I need to modify the degrees of freedom. Yes, so that's luckily I got it right. So in this case, we have two rows. So we're gonna take the numbers of row -1, which is 2 minus 1, times it by the numbers of column -1. So we got 3 columns, so 3 minus 1 is 2. So 1 times 2 is 2. So degrees of freedom is 2. Okay. So that's going to be the shortcut, and the shortcut will give you the answer for the test statistic, and they also give you the answer for p-values. Yeah, so the shortcut, the chi-square test, will give you the answer for these test statistic and the p-values. So after we got the answer for p-value, we're just moving on to step number 5, compare p-values and alpha, right? So if p-values is less than alpha, we reject the null hypothesis. If p-value is more than alpha, we fail to reject the null hypothesis. Yeah, so the same rule of decision. If p-value is less, we reject. If p-value is more, we fail to reject the null hypothesis. And then after you got the conclusion for step number 5, you're gonna answer the question of interest based on the context of the application. So there is sufficient, there is insufficient evidence. So that's going to be the test for independent. You want to determine if the row variables and the column variable, they are independent or not. Okay. So once again, if you want to use the shortcuts, everyone, you only need to input the observed matrix, the expected matrix. The calculator will calculate it for you after you run the program, yeah, or the shortcut, the chi-square test in your calculator. The calculator will calculate the expected table or the expected matrix. Yeah. Okay, so let's give it a try. We're going to use in this example to give you the ideas of how we perform the test for independent. Okay, so in a survey of 883 males and then 893 females were asked the same question. If you could have only one of the following, which one would you select? Money, health, or love? So their responses are presented in the following tables. Test the claim that genders and responses are independent. So we're going to test the claim. So test the claim. What's the claim there? Genders and responses are independent. Yeah. So we're going to test for independent, right? So genders and responses are independent at alpha is equal 5% significant levels. So we have the gender is going to be man, woman, right? So that's going to be a categorical variables. And then we have money, health, and love. And this the responses also in terms of the qualitative or categorical variable. So we survey 883 males, and then we have 893 female for this survey. So we're going to test for independent. If you want to test if the genders and the responses are independent. Okay, so we will test for independent. So take a look at this expected first, right? So you might need to calculate the expected first to make sure that all of the conditions should be okay. So I just created tables in advance, so you can do this calculation one more time there. So I need to get the total for the row, and then I need to get the total for the column. Okay. So now for men, we have how many men in total? 883. So that's the 883. And then for women, we have the totals of 893. Okay. Now for money, how many people select money in total? So we got 82 plus 46, 128. And then for this health, how many people selected health then? 446 plus 574. That's going to be 1012 or 1020. And then 355 plus 273. That's going to be 628. And now how about the table total? So which in all of the number that's inside the table, we just add them up, right? So going to be 82 plus 446 plus 355 plus 46 plus 574 plus 273. So that's going to be 1776. Yeah, so that's going to be 1776. So now after we know the row total, the column totals, and the table total, we can go back to each of the cells and calculate the expected, right? So for the first cell, we're going to take the row total, see 883, times it by the column total, 128, divided by the table total, 1776. Okay. So let's see what's the answer then. 883 times it by 128 divided by 1776. Okay. So 63.64. Yeah, 63.64. Now, similar idea for the next cell right here. We're going to do the similar calculation for expected then. Row totals is 883. Column total 1020 divided by the table total 1776. Okay, so 883 times it by 1020 divided by 1776. So that's going to be 507, 13, 507, 13. This is going to be 507.13. Okay. Now, similar idea, we can move it on to the next one, right? So expected is going to be equal row total, which is the row total will be 883 times it by the column total, 628, divided by the table total is going to be 1776. Row total is 883 times it by the column total, which is 628, divided by the table total, 1776. Yeah. So it's going to be 312.23, 312.23. Okay, now similar idea, we can move it on for the next values, right? For the next cell, we're going to calculate the expected answer. So the row total is 893 times it by the column total is going to be 128 divided by the table total 1776. Okay, 893 times it by 128 divided by 1776. 64.36, 64.36, 64.36. Now, similar idea. The next one, we have expected value right here will be row totals. It's going to be 893 times it by column total 1020 divided by the table total 1776. Okay, so 893 times it by 1020 divided by 1776. So 512.87, 512.87. Now one more to go. expected value right here will be equal 893 times it by 628 divided by 1776. So 893 times it by 628 divided by 1776. Okay. So this is 315.77, 315. Yeah, 315. Okay. So based on the calculation of the expected value, you can use it to double check the condition, right? So the first condition, make sure that the males and female that we selected right here, they're gonna be in terms of random sample. The second requirement, on of the expected values is at least one, right? So on of the expected right here is more than one. And then we don't have any observation that's on of the expected. Yeah, so we don't have any expected value less than 5. So the condition should be okay. Yeah. So that's going to be step number 3, which is done that to double check the condition. Okay, so now let's go back to your hypothesis test then. Okay, so the hypothesis test, we're going to say that genders and responses are independent. And then for the alternative hypothesis, we're going to say that the genders and the response are dependent. Okay, so they're not independent, they're dependent. Yeah. So that's going to be step number 1, we just determine the known and the alternative hypothesis. Now, step number 2, we select an alpha, right? Alpha is equal 5%. Yeah. So alpha is equal 0.05, significant level, 5%. Okay. Now, step number 3, we just calculate this expected value, and we did that already, so that should be good. But theoretically, that you don't really have to do this calculation for the expected because you might using the calculator. When you're using the shortcut, the chi-square test, they will calculate the expected. Yeah, okay. So this is the expected and the statistic right here, right? Now, step number 3, okay, so expected counts and statistic, okay. So in order to get the answer for the test statistic right here, you might use the shortcut then, using the chi-square test for metric A. Okay, so we're gonna get this chi-square sub 0. It's gonna be the chi-square of 0 equal, yeah. So we're gonna use the chi-square test and the matrix that's gonna be matrix A. Yeah, so we're gonna use in chi-square test for matrix A, so we can get the answer for the test statistic. Yeah. Okay. So before you can use the chi-square test, everyone, you have to input the observed values onto metric A. Okay, so we're gonna go to the metric A. So everyone remember that's right. We're gonna go second matrix, and then we're gonna go to edit option, and it's gonna be metric A. So this matrix have 2 rows and then 3 columns. So it's gonna be 2 by 3 still. Now the first value is 82. The second value is 446. The third one is 355. And then the next one is 46. The next one is 574 to 73. Okay. So we just input the matrix, right? Okay. Now we're gonna go second quit, and we go to the start option, and then the test, and then we're gonna go down to the chi-square test. Yeah. What's the option C? Yeah. So we're gonna go start and then test, and then go down to option C, chi-square test. Yeah. So the chi-square test. And then the observers is matrix A. Yeah, so the observer is the value that we are given from the table. You don't have to put the total, just the original matrix. They have 2 rows and 3 columns, just the original one. Yeah. And then the expected will be matrix B. So once again, if you want to call the matrix B for the expected, you're going to go second matrix and then just go down to matrix B. There we go. So we have matrix B as the expected. Yeah. And then calculate. Okay, so we have the answer for the test statistic right here is 36.8396. Yeah, so the answer for the test statistic is 36.83. Yeah. So it's going to be 36.8396. So that's the answer for the test statistic. Now, from the shortcut, the chi-square test, we also have the answer for p-value, right? So step number 4 is also done because we know the answer for p-values already. So when using the shortcut, we know the p-value is equal. Let's take a look at the output then. So it's going to be 1.0008 or 9, right? And then e to the power -8. Because this is e to the power -8, so which means that you're going to move the decimal point 8 places to the left, right? So if you're going to rewrite this p-values in terms of the decimal form, then you will have something look like this: 0.1234567 and then 1. So I can say that this p-value is very small, right, everyone? Because they have a lot of zero before the non-zero digit, right? So I can say that this p-value is approximately equal 0. Yeah, so p-value is actually approximately equal 0. This p-value is very small from the calculator. Yeah. Okay, so this is the output that we have earlier. I just show it on the screen just in case you want to double check the answer later. So that's going to be step number 4, which is using a shortcut, the chi-square test, to get the answer for the p-value. Now, step number 5, we're going to compare p-values and alpha then. So p-value is equal 0. And then alpha from step number 2, we know alpha is equal, what is it then? 5%, 0.05. Okay, so when you compare p-values and alpha, we can say that p-values is less or more. So p-values is actually less than alpha, right? So p-values is 0. Yeah, so 0.00. So that's actually less than alpha. Okay. So if p-values and alpha, if p-values is less than alpha, then what is your conclusion then? So if p-values is less than alpha, we will reject the known hypothesis, right? Yeah. So if p-value is less than alpha, we will reject the known hypothesis. If p-value is more than alpha, you fail to reject the known hypothesis. Yeah. So now, after we got the conclusion of reject the known hypothesis, then what should be your final answer then? What's your final statement to wrap up this hypothesis test? So because we reject the known hypothesis, then there is sufficient, yeah. Then conclude what? You're going to take a look at the alternative hypothesis, right? So the alternative hypothesis say that genders and responses are dependent. Yeah. So you're going to reject the known hypothesis, would mean that there is sufficient evidence to say that gender and response are dependent. Yeah. At 0.05 significant level. So that's going to be the conclusion of your hypothesis test for independent. So once again, if you want to determine if the two quantitative variables or the two qualitative variables or the categorical variables are independent. Yeah. So this is going to be the idea for the hypothesis test for independent. Yeah. So let's show you something right here, right? So for this question right here, we just complete the calculation for the expected value by hand, right? Expected frequency by hand. But actually, when you're using the shortcut, the chi-square test, the calculator already gave you the answer for the expected frequency in the matrix B. So now let's take a look at the matrix B then. So we're going to go second matrix and then go down to matrix B then and hit the enter keys. Now you can see that's going to be there's some output in the matrix B, right? So the first value is 63.64 and then 64.36. The next one is 507.13 and then 512.87. And when you can go more further to the right, you will see 312.23 and then 315.77. So the expected frequency for this table, you might try it to do it by hand, or when you're using the shortcut, the chi-square test, the calculator will help you with the output for the expected frequency for each of the cells in the table. So that's going to be the test for independence. So once again, we're going to use this test to determine if the row variables and the column variable, they are independent. Okay. So this is the chi-square test for independent. Now we're going to use the same test, which is the chi-square test, but now we're going to test for homogeneity of proportion. So what does it mean for test of homogeneity of proportion? So in a chi-square test for homogeneity, we test the claim that different populations have the same proportion. So we test the claim that different populations have the same proportion of individuals with some certain characteristic. So you want to see if different populations have the same proportion on some certain characteristic. Yeah. So what's going to be the procedure for the hypothesis test of homogeneity of proportion? The procedure for performing a test of homogeneity of proportion are the same as though for a test of independent. So the procedure is going to be similar with the test for independent that we just completed. The only thing different is it's just the way that we say the known and the alternative hypothesis. Yeah. So how we're going to say the known and the alternative hypothesis? So the known hypothesis, we're going to say that proportion are the same for all of the population. Yeah. So all of the category, we have the same proportion. Proportion are the same for all of the population. Yeah. And then for the alternative hypothesis, we're going to say that at least one proportion is difference. At least one proportion is difference. Yeah. So that's how we say the known and the alternative hypothesis. After we got the known and the alternative hypothesis, we're going to use the same procedure for the test of independent to complete the hypothesis test for homogeneity of proportion. So step number 2, 3, 4, and 5, and 6 going to be similar with the test for independent. So now let's give it a try for the test of homogeneity of proportion. You want to test if the population will different population we have the same proportion of individual with some certain characteristic. That's the idea of test for homogeneity of proportion. Yeah. Okay, so we are given a table, placebo, experience, and this kinds of medication. And this is the numbers of people with stroke, and then this is the number with people would have no stroke after they take the medication. So now tester claim that the proportion of individuals who has stroke is the same for each treatment. So we have 3 different treatment right here, and you want to test if those 3 treatments, we have the same proportion of the numbers of people who have stroke after they take those treatment. Okay. And then we're going to test at alpha is equal 5%. Okay. Okay, so test for the tester claim. So this is going to be the hypothesis, right? Hypothesis of what? That the proportion of individual who has stroke is the same for each treatment. Okay. The proportion of individual who have stroke is the same for each treatment. Okay, so that's going to be the hypothesis test. Okay. So this is going to be the observed value right here, everyone. You might need to input those values onto the matrix A before we move on, right? So I'm going to go second matrix, and I'm going to go to the edit option. And I'm going to select matrix A, and this matrix is still a 2 by 3. So 2, 3. Now the first one is 250, 206, 213, 1400, 1444, and then 1442. So that's going to be matrix A. So you might need to calculate the expected later on, or we can use it a shortcut, right? So we can try the matrix later on. Yeah, okay. So let's complete the expected then. So we need to get the total. And we need to get the total right here. Okay. Now I need to get the row total first, right? So going to be 250. Sorry. I'm going to quit from there. So going to be 250 plus 206 plus 213, 50, 06, 13. Okay, so that's going to be 669. Now the next one is going to be 1400 plus 1444 plus 1442. Okay. That's going to be 4286. Okay, 4286. Now I need to do the column total, right? So going to be 250 plus 1400. Going to be 1650. Yeah. Now the next one will be 206 plus 1444. That's going to be 1650 answer. Yeah, 1650. How about the third one? It's going to be 213 plus 1442. 1655. How about the table total? The table totals, we're going to add everything in the table. 250 plus 206 plus 213 plus 1400 plus 1444 plus 1442. 4955. 4955. Okay, so now we are ready to calculate the expected right here, right? Okay. So for this expected value, once again, we're going to do the row total, column total, and then divided by the table total, right? So the row total will be 669 times it by column total will be 1650 divided by the table total, is 4955. Okay. That's going to be 222.77 to 222. 77. Okay. Now, similar idea right here, we're going to calculate the expected then. So expected equal row totals, which is 669 times it by the column totals, it's going to be 1650 divided by 4955. 222, again, the same value. That's going to be 222.77. Now, the third one will be kind of similar idea. So the row total will be 669 times it by the column 1655 divided by 4955. 223, 22345, 22345. Now similar idea, we can complete for the second row, right? So gonna be row total 4286 times it by 1650 divided by 4955. 4286, 1650, 4955, 1427, 22, 1427, 22, 1427, 22. The next calculation will be the same also, right? Yeah. So this expected value will be also 1427.22. How about the last one right here? We have expected values equal. So the row total will be 4286. 4286 times it by 1655 divided by 4955. Okay, 1431.55. 1431. 14.31.55. Now, based on this calculation for the expected right here, right? So we see all of the expected values are more than 1. And then we don't have any observation of expected frequency less than 5. So the condition for this hypothesis test should be okay. So we're just moving on and do the hypothesis test then. So we're going to say the known and the alternative hypothesis. So we can say that for the known hypothesis, we can say that the proportion of individual who has struck A the same for each treatment. Yeah. Okay, so for the alternative hypothesis, we can say that at least one. Yeah, so at least one of the proportion is difference. Yeah, so at least one of the proportion will be difference. Yeah. So that's how we say the known and the alternative hypothesis for the test of homogeneity of proportion. Different population, we have the same proportion. Now, step number 2, we're going to select an alpha 0.05. That's what the question gave us. Alpha is equal 0.05. Step number 3, we just calculate expected and then test statistic. We're going to use a shortcut to get the test statistic then. So using the chi-square test for matrix A, I'm going to use in this notation then chi-square sub 0. Okay. Okay, so now we're gonna use in this test right here, the chi-square test. Okay, we're gonna use in the chi-square test. To double check the matrix A, everyone, make sure that you got the data onto matrix A. Yeah, just go to the edit option, double check. Yeah, so the 250, 206, 213, 1400, 1444, 1442. Okay. Now after that, we go second quit, and we're gonna go stats, and then we're gonna go test, and then we're gonna go down to option C, chi-square test. Yeah. And then the observed will be metric A. The observed value we input in metric A. The expected will be metric B. Yeah. And we're gonna go down to the calculate. Okay. So the chi-square 0, which is the test statistic, is 5.8718. 5.8718. And then how about the p-value we got there? Okay, so when we're using a shortcut, we also have the answer for p-value, right? So p-value is equal, what is it from the output then? 0.0531. So p-value is equal 0.0531. That's the answer of p-values. Okay, so now we are ready to compare p-values and alpha, right? Okay. Okay, so let me drag the output right there so we can have the answer for you guys to compare later, just in case. Okay, so this is gonna be the output that we have from the chi-square test, right? So this is the output that we have from the chi-square test. So we have the test statistic is 5.8718, and then the p-value is 0.0531. Now we're gonna compare p-values and alpha then. So p-value is equal 0.0531. And then alpha from step number 2, we know alpha is equal 0.05. So p-values is a little bit more, right? So p-values is actually more than alpha, yeah. So p-values is actually more than alpha. It's a little bit more, yeah. So p-values is greater than alpha, then what's your conclusion then? So p-value less, we reject. If p-value is more, we fail to reject the known hypothesis. Yeah. Okay, so we fail to reject the known hypothesis, which means that the known hypothesis is still true. If the known hypothesis is true, which means that the alternative hypothesis is not true. So what's going to be your final conclusion then? So for the final conclusion right here, we're going to say there is insufficient, right? Evidence to conclude that. Concludes what? It's going to be the alternative hypothesis, right? So we don't have sufficient evidence to conclude that at least one proportion is different. We're going to copy the alternative hypothesis. Yeah. At least one of the proportion. Yeah, so I'm going to say at least one of the proportion is different at 0.05 significant levels. Yeah. So that's going to be the conclusion for the test of homogeneity of proportions. So for this section 12.2, we have the same shortcut, which is the chi-square test. But the chi-square test that we have, we can use it for both of the hypothesis tests, right? So we can use the chi-square test for the test of independent, and then we can use the chi-square test for test of homogeneity of proportion. So this is gonna be the conclusion of section 12.2. So I will stop the sharing at this point. So once again, we have the chi-square test for this recording, and then the chi-square test, we can use it for test of independent and then test for homogeneity of proportion. So you might stop the recording at this point and try some homework question on chapter 12. I will see you next time for the next recording.